When thinking about simple regression, there are 5 conditions that we must check. The first one should be familiar. We are always required to have a random sample, or at least a representative sample. If we can't take a random sample, we want our sample to be at least reasonably representative of the population, but ideally a random sample is best. The second condition that we must satisfy is that we have a quantitative response and a quantitative explanatory variable. As I said at the beginning of the semester, if we're able to identify the kinds of variables we have, whether they are quantitative or categorical, that tells us immediately the kinds of analyses we can and cannot do, or the kinds of methods we can use. In this case, if we have a quantitative response and a quantitative explanatory variable, that means we're automatically going to be able to talk about linear regression. The third kind of assumption should also be familiar. Because we want to do a t-test, we know that we have to have a t sampling distribution for our sample slope. In order to use the t distribution, our population response, the population of our response must be normal. We saw this when we were talking about the one sample test for the mean. However, now because we have a quantitative explanatory variable, the population response must be normal at all values of that explanatory variable. So what does this mean? It means that, for example, we have in this plot a plot of distance, our response variable, versus speed. If we're thinking about the stopping distance the stopping distance based on the speed of a car, so how long or how far a car needs to stop based on the speed it's traveling, we can imagine that if a car is traveling about 6 or 7 miles an hour, the distance must be approximately normal for those speeds. Similarly, if cars are traveling about 20 miles an hour, the stopping distances must also be normal, follow a normal distribution. So we can kind of think of this third condition as really subsetting the population across all these different levels of that explanatory variable. As another example, think of talking about predicting children's heights based on their ages. We know that there is a general population of children who range from maybe 2 to 10 years old. But we can also think of the population of children who are 2 years old, and the population of children who are 5 years old, and 7 years old, and 10 years old. What this third assumption is saying is that for all 10-year-olds, so for all children with the same value of the explanatory variable, so for all 10-year-olds, the height must be normal. It's also saying for all 7-year-olds, the height must be normal. And for any age that we can think of, the distribution of height must be approximately normal for this t-test to work. So however we subset it, or for whatever subset of the population of children, for example, the distribution of heights must follow a normal distribution. And these are 3 conditions that we're familiar with. We're always going to talk about having a random or representative sample. We're always going to think about what kind of variables we have, and we're always going to have some sort of distributional assumption. The next 2 conditions are unique to regression. The 4th condition is that the distribution of the response has the same standard deviation at all values of the explanatory variable as well. So when we're thinking about that normal distribution, it has to be spread out the same. So if we come back up to this plot up here, we can see that for cars that are traveling about 7 miles an hour, the spread of the distances is the same as for cars that are traveling about 15 miles an hour, and is the same as the cars who are traveling about 22 miles an hour. So no matter how fast cars travel, the variability in the response around that regression equation is about the same. We're talking about spread now. So not the shape. The shape is talking about normal. We're not talking about the scatter around the line. So the scatter around the line must be constant. And we'll talk about how to check conditions 3 and 4 later on in another video or in class. This fifth condition is that the linear model, so this model that we're talking about in the first place that allows us to talk about a constant change, so that as x increases by 1 unit, we always have that same change in the response, is appropriate in the first place. And we check that by using a scatter plot. So for example, I would look at my scatter plot of heights versus ages, or I would look at my scatter plot of distances versus speeds. And if it looks like I have a roughly linear form, then my linear model is appropriate. That's how I would check it. If it looks like there is some sort of curve in my data, then it would not be appropriate to use a linear model, and I would have to use a different model of a different form, perhaps a curvilinear model, or I might have to transform my data. But in order to talk about linear regression, and in order to do a linear model, then a linear model must be appropriate. I would not want to draw a straight line through these data because that would not be a good fit. So those are the 5 conditions for regression: that I have a random sample, that my response is quantitative, and that I have a quantitative explanatory variable, that my response is normal at all values of the explanatory variable, and that the response has the same standard deviation or spread at all values of that explanatory variable. And finally, in order to do regression in the first place, my linear model must be appropriate. It must look as if I have a linear form.